Hey, what's going on, everybody? So for this final video, we're going to cover the appendix items for this presentation. I'd say there's about 13 or 14 slides, and they pretty much just cover all the glaring items that were missing from the presentation that would have come up during the defense. So there's a few items that I thought was worth mentioning. The first being the use of a training set. So naturally, when you think of a classic machine learning, deep learning application, you have a training set, which is usually the vast majority, something close to 70 or 60 to 70% of the full model is dedicated to training, as the model really needs to tune those weights, compute loss, and then forward and back propagate. Additionally, we have a validation set, which is used to actually validate the model as the model is training. Is it actually converging or not? That's just because it's very easy to overtrain on that training set. So the validation is that sort of test as the model is learning, and the test set is sort of the final. Is the model better than alternatives? We separate the test set from the validation training set. Otherwise, you get overfitting. The model has seen the test set if it's included in some way and incorporated in the other splits. So it's worth mentioning that the lack of a test split provides more training for the model training. So this is just because when you're executing these malware snapshots, it's like kind of prohibitively expensive because there isn't really, I wasn't able to fully flesh out a good automated way of doing it. Examples are expensive, not like costly expensive, but just there wasn't really automated way, and the use of the Cuckoo sandbox didn't actually do everything I wanted to do. The testing set can be considered the manual testing against viral toolset. So this is something that I fleshed out more so in the paper thesis, which is that when I tested on the when I trained on the training set, use the validation set to actually see my losses and accuracies. F1 scores were increasing, as they should, as the model learned. The final test set for me was actually compared my model and looked at the APIs it was generating and see if it flagged any of the malicious processes and executables. And then I actually looked at the same executables that were run on the VirusTotal sandboxes. So the VirusTotal API and even the website, you can actually drop in an executable there and have a offline sandbox honeypot and more of a dynamic malware tool actually look at the executable that you've dropped in and actually can tell you, did it identify any behavioral signatures that it can consider malicious. So that was the testing for this work. Additionally, this model isn't an attempt to be production ready. It's not something that you'd want to push out. It's a proof of concept, and that's mainly due to that feature extraction, that last point where we extracted a certain API sequence from the behavior of metamorphic malware, and we corresponded to a MITRE technique, and we used that in some form of signature based technique, or we can just feed it back into the model. Ultimately, when you're training a model and you're generating these sequences of APIs, the model has learned to understand that these sequences of APIs are malicious, and they're malicious identifier of malicious behavior. So that was the training set. Security journal scope. This is something that came up, which is the literature review I was doing. Didn't have much of a security scope. A lot of it was based on the deep learning, machine learning literature. So a question that had come up continuously was, what is the coverage of this thesis when it comes to like its subjects and domains? So if you take a frequency analysis of the top 10 most frequent keywords in the publication name. So that's one indicator is, okay, let's look at all the publications, look at the publication names. What words do we see? Besides just tossing out all those filler words, like the ands and the adjectives, what do you see? You see security, computer information, computing systems, so on and so forth. So this is just based on the publication name. Publication title. Okay, so publication title is actually like the name of the paper. Publication name is the journal conference proceeding. So keywords by publication title, detection, malware, analysis, learning, intrusion, all those hot button words. So like I said, publication name, top 5 publication title. So TLDR, malware detection within a security scope. So that's something that I figured would come up. State-of-the-art comparison, something that comes up naturally in any work is, you tested your model and you determine it's better than the vanilla. Okay, well, if yours is state-of-the-art, why aren't you comparing it to other state-of-the-art models? And that's a good That's a good question. This is just to demonstrate that at least in this work that I'm doing so far, it's a proof of concept. What questions does it answer? Well, can we draw actionable insights from GNNs? Answer is yes. Yes, we can score and flag highly scored binaries and extract these subgraphs and look at those MITRE techniques. And we can do so through highly impactful API calls. Again, it's not that API calls and sequences and n-grams hasn't been done before. It's not like GNN is a stranger tool in the malware community. If anything, the complexity model and the way that we extract features is the novelty. Word embedding vectorization. So on the right here, we have our bag of words, and for each node, H1, H2, H sub 3, we have a one hot encoded for the APIs that are used. So something that potentially came up is, okay, so you're just taking these features, you know, in the natural language space, there's plenty of different ways that you can create these rich word embeddings, right? High order feature space, GPT-3, GPT-4. From my understanding, it has something close to maybe a size of 500 of an embedding space, right? This is just to point out the more advanced ones like glove can carry rich semantic information about the vector space of those words, but it's difficult to converge for sparse data sets. So if you have what we have on the right here, and we have lots of APIs, but very few ones, that's a very sparse data set, right? Few and far between. So it's very hard for these embedding techniques to actually learn the associations just because the APIs aren't used enough. And to train these word embeddings for it to be useful, you need, it's hard to say, but you need something where you have a corpus, Wikipedia, the internet to train on words and how they exist and the context that they're used with other words. You need a very large data set for that. For the data sets that we're working with, it's just very difficult. And one thing that I noted when I was testing this in previous work was, I think it's this embedding dimension here, was we found model accuracy. So the parameters go up as the model, you add more complex capacity to the model. DE is this embedding space. Higher order embedding space kind of has a rate of depreciating returns. So we're taking these API calls and we're stretching in this 300, or actually it's 50 to 150, 200 embedded feature space. And what we find is that the model isn't learning anything new. You're adding complexity, but it's just making it confused because these APIs don't appear next to each other with such a frequency that the model can learn that rich semantic information. So for that reason, word embedding techniques like glove weren't used, and we just left it as the raw feature vectors. There's maybe a question about, actually that came up even in the original presentation, was how this inner working of the graph attention works. So there's a few things that are added in this model that weren't discussed, but they're fully kind of covered in the full paper, which is that dropout is used in the model. So dropout here, dropout there. What is dropout in effect doing? Rather than forward propagating and even back propagating all the models at each during each feed forward, dropout will take some of those neurons that are being fed in and randomly drop it, so that the neurons in the after layer are learning to not kind of place too much importance on certain neurons to make its prediction. It adds a little bit of stochastic nature to the model. This, in effect, is learning an ensemble of models as it's learning. How is that? Well, when the model is fully connected, you're learning a certain one type of architecture, the architecture that you initialized. When you have dropout and you're dropping out 50% of all the neurons, well, your model is learning a network that has 50 of its neurons that don't exist. So the neurons are seeing different when it's performing the forward propagation sum. For that net input sometimes is very different because certain neurons that thought it were important don't exist. So the model learns to learn different model architectures as it goes. And what we found out was why dropout is used very widely is that it's a very good way to avoid overfitting. And that's just because you're also learning very different sets of models as well. So we still have this feature vector that comes in, weight feature matrix, to learn those embeddings, dropout. Then you have this space here, which is how we actually learn those activations. We have this exponential function on top, exponential function on the bottom. If you really want to deep dive in it, you'll see that you have this learnable weight W times H, which is right here. So this is the original. Okay, sorry. So the H is here. This is almost like a weight matrix here. So this H is multiplied by the weight, and then we double pipe operator with between I and J. So we're computing those. So for two different nodes, right? We compute their WH, and we concatenate them. When we do that, we multiply it by this weight, the weight vector, which is right here. And then we compute the ReLU, and then we perform a softmax. Okay, so the top here is the same as the bottom there. The only difference is the sum of the exponentials. So all this around here is actually performing the softmax to give us a value between 0 and 1. So it's actually computing an activation for a node and all of its neighbors, and computing an activation such that the activation sums over all those nodes sums up to 1. And that's because it's doing WH sub I of J and all the other neighbors. See K as an element of the neighbors of I. And then you sum it, and then okay, so once that's done, sum it, non-linearity, and then we end up with our final activation. So all this alpha here is kind of summed up there, and then this was discussed during the presentation of how we actually take that activation value and multiply it by the weight in H. Neat stuff. This is something that naturally would come up, which is you have this complexity layer. You know, Ken, I looked in the paper and there's all these different values. Why did you choose this? Why did you choose that? I mean, it just seems like you came up, you just threw this complexity layer with all its parameters already set. And the answer is, well, actually in this previous work, we tuned these parameters of the complexity layer. This is a couple years back. We noted that the measure is actually highly sensitive to the embedding space. What did we do exactly? For one parameter in particular was the Minkowski order of the norm, which is this Minkowski order of the norm is whether or not you're computing the distances in Euclidean space or higher order differential space, or the Minkowski distance, so Minkowski order of the norm, or the Manhattan distance, Euclidean, or any higher order feature one. So there's different ways that you can compute that distances in embedding space. And as a result, you can also vary that between 1 and 5. So if you test different ones over different Ks, and Ks is just a whole nother thing with when we're computing a complexity layer, you're considering more and more subsets of the nodes. So a K of 2 would be considered a 1 subset, 2 subset in complexity. K equals 5 is take 1, 2, 3, 4, 5, and then compute the complexity. So there's lots of tunable parameters. And this has all been fleshed out in this, and we looked at all the assortment of different ways that you can tune the model and came up with one that performed a high validation accuracy. And there's also some testing done in the actual thesis itself. So here's something that comes up naturally, which is why use the complexity layer at all, right? So you have a vanilla layer, which does include complexity. There's obviously a cost to the complexity, incorporating it. There's obviously a cost of me working on it. So, okay, so you have this setup. Why do we want to incorporate it at all? A couple things. One being space complexity, a comparison of space complexity, one being the time complexity. So one thing to note is that in this plot up here, we have all the different layers of a model, dimensions, input, outputs, number of parameters, estimated size in kilobytes. Things like the GAT-conv and the linear layer are part of the vanilla layer. They're simple convolutions over the W transpose H. For these larger ones, we're looking at over 1 million parameters, large file size. The fractal dimension in of itself, because it's something that's computed on the fly, it's not stateful at all. You actually only need 1 parameter. And that's just because you're computing complexity of the embedding space in the feed forward and then feeding it in, and you just need to store that weight. You can see that in terms of the uses of, at least for space complexity, the fractal dimension layer is negligible. Now, in saying that, we have the stateless layer, and it's computing on each feed forward, right? So what does that mean? That means that there's a cost associated with runtime. So for each of our forward methods in milliseconds, mean and standard deviation, We found that as a function of input feature size, input feature sample space. So what's the difference? Input feature size, input sample size. Feature size, sample size. I think this was, the feature size is the number in the corpus. Yeah, so that would be the dimension. And input feature size is how many training examples. So in one feed forward network, computing that embedding, you know, it kind of scales linearly. And that's because I do have the runtime complexity that I did show at least in one presentation previously, but obviously there's a cost to it, and it just scales kind of nicely with the size, the input feature size. So it scales linearly with these parameters. But ultimately, the point is this is not negligible, right? So that's where the cost is in that runtime complexity. Computing it can be cost prohibitive, and ultimately this is because this distance matrix is costly for each feed forward pass. There's ways that you can remedy it by including some running sums and seams, or running means and running sums. But as a simple metric, it's a very simple with a computational graph for computing gradients. It's not too sophisticated to make that computation and feed it in. So it's simple in that respect. Let me go to sort of the measure of complexity. So the thing is, I talk about complexity and how it's a very good feature extractor, fairly highly compressible. So one thing to note is that the measure is highly sensitive to changes in the feature space, as noted in 2021A. So this is in the previous work. We looked at, I think I did mention this presentation, but if we have a feature set with these green and red dots, and we computed the complexity of these green dots, and then we added these red dots and computed complexity, ideally, because we're just looking at the spread, at least to the naked eye, if you didn't see the colors, you would say that these are all part of the same blot, right? Because this is produced in a normal distribution around this centroid. But one thing that what we found was that if these weren't colored and you computed the complexity of the green and computed the complexity of the green and the red dots, there was a discernible difference, a statistical difference, such that the complexity there can tell the difference of these spreads. Okay. And the model is trying to minimize this loss. So honest to God, this isn't the best illustration for what this slide is trying to tell us. But we can say that the highly nonlinear embedding space is fine-tuned by the model to create a nonlinear hyperplane to separate the training examples. So ultimately, that's what the model is trying to do, right? Create that nonlinear feature boundary in this higher order feature space. And the complexity layer, by computing this spread, is telling the model about that. So this was covered in the slide, but just thought maybe I will flesh it out in an additional slide. Benchmark data sets. I'm actually just going to skip this because originally this wasn't included in the first presentation for the committee. So this is just to summarize that. What is the differences in benchmark data sets? Number of nodes, number of edges. Highly connected nodes, number of edges becomes oversaturated very quickly. This is a good point. We have the Facebook page data set. It has tons of edges. What does tons of edges mean? That means that in particular pages, you could have an edge to one different page, and that page could have an edge to another one. And the likelihood that that page is also linked to the first one is very high. And that's just because we have, for the number of nodes and number of edges, you can kind of see that it's more than tenfold, right? That means for every one single node, it has over 10 or 11 edges to other ones, right? So you can imagine that in the graph neural network, when you're learning about the behavior of your neighbors, then you can see how it's very quickly all the nodes in this relatively small space, in topological sense, becomes oversaturated. It's pretty much the model has learned everything it needs to know about the graph. Each node is fully saturated, has the same information because it's seen all the other nodes in the whole feature space. So that's one of the other reasons why it performed poorly. And that's because of the depth of the GNN, where we considered 2 layers. And then additionally, high number of features benefits from more complexity increase the width of the GNN. I think this is kind of interesting. What's feature? It's kind of just to say that when you have these highly connected nodes, when they are totally connected like that, then the models perform poorly when you have deep GNNs that have multiple layers. Okay, neighbors of neighbors, neighbors and neighbors, right? But when you have a high number of features, like in these 2 examples, the model performs better with maybe not so deep networks, but kind of, so not deep, but kind of wide. So high number of capacity for each of the hidden layers. And that's just because you need that capacity to learn these features, as opposed to you need the depth to learn the nodes and the edges. So it's kind of like you stretch it out this way, depth, width. Depth is the number of layers and the number of hops. Width is the number of capacity and the size of that embedding space. The complexity layer does very well with computing higher order feature space and differences in the embedding space. So when you have high number of features, that's when it performs well. And the complexity layer actually doesn't do much good in these cases because the complexity layer actually doesn't touch the nodes and edges connections. It doesn't do anything like that, right? So for that reason, it's almost negligible compared to the vanilla model. Additionally, one thing that came up very naturally in this work was, actually it makes sense just to look at this bottom plot here where we could have been testing two different event types. And then we see this NS that comes up very often in the tables in the thesis. NS being just non-significant, actually I kind of summarize it here where elements bolded, blah, 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 blah. NS signifies not statistically significant, where P is less than 0.5 from their model counterparts according to T-score. So that's just the statistical measure for saying if two different independent variables or sort of distributions, if they're statistically significant, then there isn't a huge overlap with their tails. And this just has to do with sampling from process executions that have static graphs with a limited number of nodes. So for example, if we have a particular node topology here, these are the exact same topology, okay? The only difference is that we have to separate the same topology in a node and a validation step. So what does that mean? That means in the training step, we want to gather, let's just say 70% of all the nodes and edges to use for training. And then in the validation step, we want to use the other 30%. So obviously some nodes are going to be part of the training, some nodes can be part of the validation. For those that are part of the training and validation, we can't use the other ones because then you have leakage from the training to the validation set. One thing to note is that when you have certain nodes, and you don't have too many nodes in this, right? But let's just say that for the sake of argument, we have a malicious executable that executes and spawns daughter processes. If in the training and validation set, we were to grab randomly the main executable malware that's executed, but in the training set, we didn't include the daughter processes. What does that mean? That means in the training set, we actually never see those daughter processes. So when the deep neural network is learning its hops, okay, it actually doesn't see the daughter processes. So this kind of only works when you can see all the nodes that are relevant, right? So as a result, or conversely, let's say it's the opposite. You execute a piece of malware, it spawns daughter processes. But in the training set, you didn't see the parent, you just saw the daughter processes. What does that mean? That means the parent process, which probably has all the behavior of maliciousness included, all the rich APIs, the model will never see it. So as a result, remember, we're also testing 18 different models. How many did I say? I don't quite hear. I don't know if it was 18 or 30 for the sake of statistical significance, but we'll just say it's 30 right now. When you're testing 30, testing 30 different model initializations with the graphs. And in some of those models, the parent process and all the daughters of the malware are included. And in some other examples are not. So in some models, it says, oh, I did very good. Well, I did very good at classification. In other ones, it said, I saw the daughter, didn't say the parent. Now I don't know how to classify malicious examples. So this just happens to do with the nature of the sampling space. Ultimately, you want as many samples as you want so that your training is rich with the positive and negative training samples. Your validation is the same. You don't have one certain type in the training and another different type in the validation, because then you're going to get poor accuracy. So ultimately, it's because sampling practices does not sample the same nodes and edges, introduces bias. Noise in the expected results, consequence of sampling missing important nodes. Repeated iterations smoothens over this effect, but at the same time, it still leads to these kind of erroneous results where you see the difference between 88 and 90, but if they're not statistically significant, then you can't be confident that they're different. I think this maybe is the last slide, which is discussion of this complexity of the inner layers. So I've mentioned this a few times, that you have the first layer, the second layer, third layer. As the layers go on, you're getting these higher order, highly nonlinear feature spaces. We found that complexity layer seems to be less effective at these intermediate layers. And that's because it's very highly nonlinear. One thing we did note, the complexity was shown to be more effective at high dimensionality. So this just goes to the fact that the complexity layer is doing a certain something. It tends to be better at computing the complexity at these early layers where it's not so highly linear. But if this layer, rather than it being 2 dimensions, is 8,000 dimensions, we found that the complexity layer did very well in computing and measuring spread in this, and small changes in the spread in d-dimensional space only becomes better. So this model almost, or the complexity layer, almost works both for shallow GNNs and very wide GNNs with large capacity and that extent. More effective at high dimensionality. Yeah, that's the exact same thing. Maybe I was going to say something different. I think it was just the opposite. Effective at high dimensionality, and perhaps not effective at deep neural networks, which is what I was trying to say. Okay, so with that, that's the final section, final slide for this PhD thesis presentation. Next series of presentations is just going to be a code deep dive into the inner workings of these layers, and sort of setting up these samples and setting up the ML flow for model learning and all that kind of stuff. So if you have any questions, please leave those in the comments. I'll be able to get back to you. And as always, thanks for watching.